So I was rewatching one of Grant's videos on linear algebra the other day when I stumbled into a really interesting problem. The video I was watching was the determinant, which is chapter 6 of his Essence of Linear Algebra series. And towards the end of it, Grant starts covering how the determinant is actually computed. After giving some of the intuition, he just quickly shows a more precise definition on screen. Now, when I first watched the scene, I, like many of you probably, absolutely paused it just to ponder it for a bit and appreciate it. But over my most recent watching of it, I noticed that Grant actually says something that I find to be almost out of character for him. And it sent me down a really deep mathematical and geometric rabbit hole. Here's what he ended up saying.
Now, if you feel like computing determinants by hand is something that you need to know, the only way to get it down is to just practice it with a few. There's really not that much I can say or animate that's going to drill in the computation. This is all triply true for three-dimensional determinants. There is a formula, and if you feel like that's something you need to know, you should practice with a few matrices, or, go watch Sal Khan work through a few.
I was surprised by how quickly he dismissed the idea of either explaining or animating the computation by saying that there was nothing that could be done and you just had to memorize it. Granted, you won't often find yourself in a situation where you need to actually compute the determinants by hand, and the video also wasn't really designed to teach the mathematics, it was more designed to teach the intuitions behind the determinant. With that said, I feel as though understanding why the formula works is imperative to accept the idea behind what the determinant actually represents. Just a quick warning, what I'm about to go over does require you to at least have a vague grasp of the fundamentals of linear algebra, and it also assumes that you've already seen chapter 6 of the Essence of Linear Algebra by 3 Blue 1 Brown. So if you haven't seen it already, I highly recommend it. With all of that out of the way, to start us off, we're going to be picking up from just before Grant gave his partial intuition for that determinant video. Now, the determinant of a 2x2 matrix can be found using the formula A times D minus B times C. Let's say that the terms B and C both happened to be 0. In that case, A tells you how much I hat is stretched in the x direction, and D tells you how much j hat is stretched in the y direction. It stands to reason that A times D then will give you the area that the unit square turns into for the transformation. Even if one of these terms, for example B, is non-zero, you end up with a parallelogram with a base A and a height D, which means that the area is still just A times D. And a quick way to gut check that is to think about a deck of playing cards. Just because you share the deck by some amount, the volume is still the same. The same is also true if you make B 0 and C is non-zero. It just shears the square and makes it another parallelogram, but this time one with a base of D and a height of A. It still has the same volume. However, if both B and C are non-zero, the area gets changed by a factor proportional to B times C. Loosely speaking, the B times C term tells you how much the parallelogram is being scaled in that diagonal direction. So this is where Grant's explanation for the intuitive way of thinking about the determinant's B times D term ends. If you're like me, that last part kind of left you with more questions than answers. And this is when he provides that beautiful diagram for those of us, quote, hungry for a more precise description, along with a pre-simplified form of the determinant equation we started with. This diagram perfectly represents the geometric derivation of the formula by breaking the dimensions up into simple shapes with known areas. Let's quickly go over it. The first pair of parentheses with a plus b represents the full width of the shape on the x-axis. Likewise, the next pair with c plus d represents the full height of the shape on the y-axis. The product of those two groups then represents the area of the rectangle which circumscribes the full parallelogram. We can call that the spanned area. Next, the term a times c is subtracted from the spanned area. This represents removing a rectangle with side lengths a and c. In the diagram, this corresponds to removing the two maroon triangles. After that, the term b times d is subtracted. Doing so, removed the two teal triangles from the diagram. And finally, the term 2b times c is subtracted, which takes away the two rectangles in opposing corners. The area that's remaining afterwards is that parallelogram that we wanted. Now, if you were to expand and simplify that formula, you'll find that you are left with a times d minus b times c, which is the formula you're familiar with. I love how nicely it all comes together in this diagram, and it does a fantastic job of showing you how the formula is geometrically derived. But this does not actually answer why the term b times c represents diagonal stretching in any intuitive way. And it was originally presented to explain that. So, to see why this formula makes sense, we need to think about what's actually happening in it by breaking it down into its constituent parts. The leading a times d term represents the area of a rectangle if that original unit square was only stretched in the horizontal and vertical directions under the transformation. You can see that when we apply the full transformation again, the distance covered on the x-axis by I hat and the distance on the y-axis covered by j hat don't change. So there must be some deeper connection here. But how, you may ask, does the rectangle b times c actually fit into all of this? And why is it being subtracted? To answer that, we have to think about the problem from another perspective. And the key is to think about how you can fit that parallelogram into the same area as the shape without the diagonal stretching. That way we can actually compare the two directly. You might have a couple of guesses as to how we can answer that question, but before we do that, let's cut out everything that's not already in that target area. With that cut made, if we cut from the corner of the target rectangle to the corner of the spanned rectangle, both of which touch the remaining piece, we get two triangles who have a point laying on either I hat or j hat. Now, if you were to slide each of those triangles along the vector that it touches, you can see it perfectly fills in a spot on the other side of the polygon, which was already inside of that target area. With no other pieces remaining outside of the goal rectangle, we can compare what we have with it. We can see that there are two empty right triangles on opposing corners of that goal. Both must have the same height and width because their hypotenuse comes from that same cut. If we were to fill them in and move them so that the hypotenuse is back to where the cut was, it forms a rectangle, which you may find familiar. It's one with an area of b times c. This is because the line that we used to cut it, the hypotenuse of each of those blue triangles, had a height of c on the y-axis and a width of b on the x-axis. No matter what values you use to get a skewed polygon, its area can be found by taking the area of the rectangle with base of a and height of d and subtracting the area of a rectangle with sides b and c, which represent the amount of shearing in each component direction. It may have seemed like we were making the problem harder just to come back to the same conclusion, but it clearly shows a connection between b times c and the diagonal stretching, something that the original diagram didn't. Now, if you were really determined, the same concept can be applied to 3D space for a parallelepiped, but trust me, it is not nearly as clean as the one we just did. I have spent hours working on a similar way to look at parallelepipeds to ensure that my explanation holds up, but honestly, you don't really need to know it, and it might even be preferable to not go down that rabbit hole. If you understand the concept behind a 2x2 determinant, then you can follow a simple pattern with that in mind to find the determinant of any matrix. It will also explain a little bit more about the 2x2 determinant formula which you cannot appreciate before you cover the higher dimension matrices. So the next question you may have is, how exactly would you go about calculating the determinant of matrices with more dimensions? Let's start one dimension higher with a 3x3 matrix. Now, if you were to spend hours on creating a 3D analog of the geometric diagram we looked at earlier, wrote it as an equation and simplified it, you'd end up with a mess of an equation that looks like this. And it doesn't exactly roll off the tongue. But you can see in there that there are two ways we can actually group the terms that make it really obvious what's happening. I already have it in order to do one of the groupings, but if you're keen, I encourage you to go and see if you can find the other way in which you can group them. Anyways, doing the grouping, we are left with A times E times I minus H times F minus B times D times I minus F times G plus C times D times H minus E times G. Bit of a mouthful, but easier than the other one. After we're done grouping, you can notice a peculiar pattern is forming, and if you look at each set of parentheses, you can see that the difference in them actually looks like the formula for a 2x2 determinant. By looking for the terms in the original matrix, you can actually see it is just the determinant of a subset of the original larger matrix. Looking deeper, you can also see that each value you multiply the submatrices by is not in the same row nor column as any component of the submatrix it's scaling. And even deeper still, you can see that those leading coefficients appear in a straight line across the top row of the main matrix. With all of that in mind, we can see a clear pattern for calculating this complicated determinant. You first start at the top left corner of any 3x3 matrix you'd like, and you take the value there to start. Then, by excluding all the values in its row and column, you use the remaining components to form a 2x2 matrix. You then multiply that starting value by the determinant of that 2x2 matrix. And once you're finished with that, you move to the next value in the top middle and repeat the process, and subtract it from the result. Finally, you do the same for the last value in the top right corner and add it to the result. The final value you get when you total all of these up will give you the determinant of the 3x3 matrix. That doesn't seem too bad, but there still is one part of this that you may be confused about, and I know that I was the first time I learned about this, and it frustrated me to no end. And that's, why are we subtracting that middle product, but adding the last one? Like, where does that come from? Now, the good news is that this is the last piece of the puzzle you need to understand before you have all of the tools to compute determinants of any n by n matrix. This is one of those connections that are very easy to miss when you first start learning about determinants and are forced just to memorize. But the answer makes it so much easier to remember. Let's look back at that original 2x2 matrix, and let's apply the same pattern to it, see what we get. We first start with A, and we exclude all values in its row and column. Then we take the remaining value and turn it into a matrix, and you take its determinant. In this case, we excluded all but D, so we are just left with a 1x1 matrix. So we multiply that A term by the determinant, and then we shift and start again for the value B. We take it, we exclude the row and column, and create a matrix from what's left, in this case C, and we take that determinant and multiply it by B, and then we just subtract the result. The determinant of a 1x1 matrix, by the way, is just the value that's inside of it. It's a distance along a one-dimensional line that it represents, basically. And this means that when it comes to the 2x2 determinant formula, it's not just A times D minus B times C. It's actually A times the determinant of a matrix containing D minus B times the determinant of a matrix containing C. Now, when you're first starting to familiarize yourself with the process of adding the pluses and minuses, A nice little trick is to think about starting with the value of 0 and adding the first product to it. So you've got that plus sign there. You should now start to see that pattern that we were seeing with the larger matrices. You first calculate, you add, shift, then you calculate, subtract, shift, and so on. All that's happening in a 3x3 matrix is we continue the same pattern by adding the result of the calculation for that third value. For a 4x4 matrix, we do the same thing, but we subtract the result of the calculation for the fourth value, and so on. For any number of dimensions, you will first start at the top left, and you take its value, you multiply by the determinant of the matrix created when you exclude its row and column. You go to the next value to the right of it, and you do the same calculation, subtract the result. Then you shift, you calculate and add it to the result. Shift, calculate, subtract, shift, calculate, add, and the pattern just repeats. This means that just by knowing the 2x2 determinant formula and some really simple rules, you can find the determinant of any n by n matrix with relative ease and very little memorization. And that pretty much sums up all you need to know about calculating the determinant. I hope that watching this video was just as fun as it was for me to design. And I also hope that it helped some of you who may have been struggling remembering the formula or just at least wanting a deeper understanding of it. This was a challenge I took on for the fun of it, and also just to grow while giving me an excuse to learn and play around with Manim, which is the tool Grant uses to animate with. It was only partway through this process that I actually found out about the Summer of Math Exposition competition. And once I did, it seemed like a perfect opportunity to incorporate my side of the project and experience into an actual video. As of when I'm recording this, though, the deadline for submission is in 3 days, so I apologize if this ends up looking a bit rough around the edges, but I hope you can still enjoy and possibly learn from it. Hey, it's editing me. Geez, the audio sounds horrible. I'm sorry. I'm trying my best to clean it up. But, anyways, back to past me. Sadly, I'm a college student, so I'm always busy with something, and it's unlikely I'll be able to continue practicing making videos like this. But I know that I love science communication, and I wish to be better at it, so this was a perfect opportunity to kind of stretch out of my comfort zone and give it a shot. One last thing before I go. I just want to clarify that I appreciate Grant and owe him many times over for the work that he has done for all of us. It may have seemed like I was being a bit critical of him at the start, but it comes from a place of love, and also it just works thematically for a vaguely coherent story. I'm a STEM tutor, and I recommend him all the time to students who need help understanding mathematics better. I really do appreciate it. But that's it. I hope you guys enjoyed, and thanks for making it to the end.